Let's get started. So today we're discussing lecture 17, which is a guest lecture by Richard. If you have seen any of the CS224 videos from previous year, like 2017, Richard Sosha was also one of the instructors. He's currently working as a chief scientist at Salesforce. So this lecture is primarily about multitask learning. We'll see what that is. I don't know why, for some reason, the slides are taking so much time to load. I tried them opening locally as well in my from a document reader. Even there, they're taking time. Okay, so this slide here shows the kind of trend that has happened in ML. As we see here, initially in the beginning, we had something like machine learning with feature engineering. The features were manually engineered, like you have to collect all the features and then you train your model. And then came deep learning. With the help of neural networks, we don't really have to worry about features. The neural networks will take care of extracting the features for us and thereby reducing a lot of efforts that are needed with ML approach. And then we have deep architecture engineering for single tasks. Like there are architectures or models that are specific to some tasks. So what would the next step be from here? So right now what we have is we have different kind of models or architectures that help us in performing some task and get the outputs. Like let's say when we want to do something like translation or speech to text, we go for sequence to sequence network or something like that. But they are very much task specific. So the next step that we all could hope for would be a single model that does multiple tasks. So that would be the ideal next step. So before we discuss multitask learning, let's quickly discuss what the problems are with single task learning. So we have seen some great improvements in the area of deep learning. Like we now have a lot of data sets which are huge, and they keep coming on so frequently, and but the problem with that is that, let's say if we have if we want to build a classifier which has C number of classes, then we need a data set which has at least like 1,000 samples per class. So that's we are talking about a data set which is very specific to that task alone. But if we are aiming for more generalized AI, then what we need is some sort of continuous learning rather than a model which is very specific to the task. We don't really want a single model for one task and another model for another task. So that would lead to a lot of complications later, like at the time of deploying. If you have 10 tasks and if you have 10 models for each of those 10 tasks, it's going to have a lot of that's not going to be really efficient. So if somehow we can have one model that takes care of several tasks, that's going to reduce a lot of work. So normally whenever we are training a model, whenever we are building a model, we either start with randomly initialized weights, or we'll take a model which is already pre-trained on some data, and then we'll try to fine tune on that. So we have seen what pre-training has done, like especially for NLP in the past 2 years, like the progress that has happened with BERT and other word embedding pre-trained models, those are the things that actually led the progress in NLP over the past few years. So when it comes to computer vision, we have ImageNet, and then we have ImageNet, which is a huge data set, and that's something that has pushed computer vision forward with the help of deep learning. And similarly for NLP, we started to have similar trend with the help of what to wear, glove, and recently bird. So the pre-training is now available for NLP as well. So when compared to computer vision, like when BERT happened, and a lot of people said that NLP now finally has its ImageNet moment. So something that happened for computer vision in 2015 has, or maybe somewhere around that time, has happened for NLP in 2018. So there are several reasons for that. Several reasons for why things have been not so fast when it comes to NLP, because text seems to be more complicated than images or vision. That's because when you're working with text, or when you're working with any task that's related to NLP, the model has to work on several layers. Like it's not just that it can get its output from one way of reasoning, but it has to consider several reasonings. Like it has to think of the logical thing to output. It also consider all the linguistics and all the rules that come with it, and it should also consider the emotional state and even visual things as well. So that's one thing which makes NLP a very hard problem. And another thing is NLP also needs short and long-term memory. So this we have discussed a lot in the previous lectures. Like whenever we are dealing with text, one problem that is very hard to address is memory. Like if there's a long sentence, like which has some 30 to 40 words, and if there is some word which comes later on and that refers to another word that has come much earlier, the model should still figure out that these two words are referring each other. So that's something that's not easy. And so these are some of the reasons why NLP hasn't, the progress with when it comes to model sharing or pre-trained hasn't been as fast as computer vision in NLP. So why do we need a unified multitask model? So why multitask learning? The reason is that if we can have one model that can address several tasks, that makes a lot of things simpler. Like unified models can decide how to transfer knowledge. Let's say we have one model that is trained on some question answering data set. And whatever the weights or whatever the knowledge that the model possesses is very confined to the data set that it is trained on. So that's obvious. And in this case, it is very much confined to the question answering data set that it is trained on. So instead, if there is a model which is trained on multiple data sets, which come from which come with very different contexts, then that would give us better that would give us a better model which can transfer knowledge better. So these are some of the advantages that come with multitask models. One is they can easily adapt to new tasks better than the single model approach, and they make deploying much simpler. Like let's say we have one model for question answering, and then we have one model for sentiment analysis, and then we have another model for another task like named entity recognition. So for these three tasks, we have three models, and if you need all of them at once, then the deployment has to be done for all the three models separately. So for each of these models, again, they'll have their own complications. But instead, if we can have one single model which does all of that for us, then that's going to help us a lot with reducing the efforts that it takes to deploy these models. And also, it kind of lowers the bar for more people to solve new tasks. And then it probably moves towards continual learning better than the single model approach. So here are some examples like how we can use a certain architectural model for several tasks. Like here we have a sequence-to-sequence model that can help us with mission translation, summarization, question answering. So this is 3, and then we have something. Okay, we'll get to that. These are considered to be the 3 super tasks of NLP. Can you hear me?
Yes.
Okay, yeah, thanks. So language modeling is something that helps us in predicting what comes next given the context so far. Question answering is obvious from the name, like given a context, and if you ask a question, the model gets you an answer. And then we have dialogue systems as well. So these are considered to be like the super tasks of NLP. So here's the interesting thing. So DECA NLP. So there's something. This is going to be this is something that we'll be discussing for the rest of the lecture. So what we have here is, if you see, normally we have different tasks like we have question answering, we have machine translation, we have sentiment analysis. Now, what this approach does is that it tries to address every task as a question answering task. What we have here, let's pick the first one. We have a question, we have a context, and then we have the answer. So what the context is nothing but the input that is being given to the model, correct? So the context is okay. Someone's not on mute.
Oh, sorry about.
No problem. Yeah. So we have the context here. Southern California is a major economic center for the state of California and the US. And what we're doing is we are asking the model a question. What is the major importance of Southern California in relation to California and the US? And then the model comes up with this answer, major economic center. So this is an example of a question answering task. So we are giving the model a question and we are giving the model a context. And then the model gives us this answer. Now let's go to the next example. This is a translation example. So what's happening here is that we have a sentence in English. Most of the planet is ocean water. So that's our input sentence. And instead of giving this to a sequence-to-sequence model and expecting the model to give us the translated text, in this approach, it is rather taken as a Q&A task. So what it does is the model is given this data, most of the planet is ocean water as the context, and then along with that, the model is also given this question, what is the translation from English to German? So here what we're doing is we're giving the model this sentence, and then we are asking the model, what is the translation from English to German? And then the model produces this output, which is the translated text of this English sentence into German. So similarly, we have another context here. We have a sentence. And this time what we're asking the model is, what is the summary? And then the model generates this as a summary for this sentence. So I hope this is clear. What we're doing here is instead of taking each of these tasks as different tasks, like one task is question answering, one task is translation, and another task is summarization. In this approach, what we're trying to do is we are trying to address all of those tasks as question answering tasks. So that's what is happening here. And like we have seen 3 examples here for 3 different tasks. We have other examples for other different tasks, like we have sentiment analysis here and other things. We'll be going through each of them soon. So yeah, these are all the tasks. So we have question answering, we have machine translation, summarization, natural language inference, sentiment classification, semantic role labeling, relation extraction, dialogue, semantic parsing, and common sense reasoning. So these are all the tasks that this model is trained to do. So multitask learning is question answering. So that's what it says. So here, all of these tasks together are being handled as Q&A tasks. So we use a question queue as a natural description of the task. So instead of saying, okay, this model is going to take an input in English and then produces an output in German, what we're doing is we give some text to the model. Along with that, we also give some question queue to the model, and the model has to automatically figure out what the task is from the question, and then it has to produce the output accordingly. So that's what this approach does. So what kind of differences do we have here? What are the specifications of such a model? So if we are trying to build a model which is not specific to any task, but it's something which generalizes for several tasks, like in this case we have 10 tasks, we don't really want to have any modules in the model which are task specific. That's what we are trying to get rid of, right? So there shouldn't be any kind of task specific modules in the model, and it has to generalize for, like, if instead of working for one specific task, it has to generalize and work for several tasks. Like in this example, we have, like here we have 10 tasks, and the model is expected to work for all of these 10 tasks the same, without any changes, like without requiring any separate model for each of the tasks. So this is how the network looks like. It's called Multitask Question Answering Network. So here we have a context at the top. I hope you're able to see this. And we give this context to this model, and then let me zoom in a bit. I think so we have a bigger slide there. So I'll finish this slide first and then go to the next. So we have the context here, which will be one of the inputs that goes into the model. As we can see here, along with the context, the model also takes a question. So, and then, so the model takes a context, and then it's given a question, and then this model generates the answer one word at a time. So there's something called pointer switch here. So what exactly does that does? So all the information that the model sees in this kind of network is, one, the question that it is given, and then the context that it is provided with, and also there is something called vocabulary that it could make use of if it needs. So these are all the three sources from which it can learn things. So pointer switch is something that enables the model to pick information from all of these three sources. So this is how the architecture looks like. On the extreme left here, we have the input, the question, and the context. So as we have seen in the previous example, the question could be a sentence in English. The context could be a sentence in English, and the question could be, what is the translation of this sentence? What is the translation of this English sentence in German? So that's one example for a question. And the model takes these two together, and then there is some sort of initial encoding where these inputs get encoded. And then we have something called co-attention. And then we also have transformer layers. And then we have different attentions here: question attention, context attention, and there is some context pointers. So these are all the things that the model makes uses to learn the things. So this is the initial input. The question and the context are being given to the model, and then there is something called co-attention. I didn't really look into what exactly it does. And then we have the transformer layer. So if you see here, we have a multi-head, and then we have an FFN block. So this is something we are familiar with. We have discussed this in the previous lectures, where multi-head helps us with attention. So this gives us the encoding. And then we have another multi-head block here. So finally, overall, this is how the network looks for multitask question answering. Okay, so how exactly does this work? So as mentioned, we have 10 tasks here, like question answering, mission translation, until pronoun resolution. So we have one model that is doing all of this. So how does how is the model getting all the data? So what they have done is for each of these tasks, they have taken the data sets for that come with them. Like for question answering, they have used the data set squad data set, and for machine translation, they have used something called IWSLT, and for summarization, they have taken another data set. So this is how they have collected all the data for all of these tasks, and they have brought them together. And these are all the metrics that we normally use for evaluating each of these tasks. Like when you want to evaluate machine translation, we normally use the blue metric. Similarly, we have the other metrics for other tasks as well. So we have these individual metrics for each of these tasks, but what we're not really working at the level of individual tasks. We are working at all of the tasks together. We don't really have single model for each of these tasks. We rather have one unified model which is trained to do all of these tasks together. So that calls for that actually needs its own metric, and Deca score is something they have come up with, which gives a score for the sum of task specific metrics. So we have all these tasks, and Deca score is something which gives us a sum of all of these task metrics, and thereby helping us in evaluating and comparing different approaches. We'll see, yeah. So here, what we have is we have all these tasks on the extreme left, the data sets that are used for different tasks, and then we have the results that are reported for single task and for multitask. So what we have here, what I just highlighted, there are different architectures. So S2S is seek to seek, and plus self-attention is when you add self-attention for that, and similarly you also add experiments are done with co-attention, and experiments are also done with question pointer. So these are different settings, or these are different configurations of the models that the authors have experimented with, and they have reported the results that they have observed for different tasks. So when single task is performed, like each of these models, like here, let's pick the first one. We have the squad dataset, which is for question answering task, and they have trained a sequence to sequence model, and they have seen this score of 48.2. And when they have added self-attention, they have seen that the score has changed to 68. And these are the different improvements that they have seen with different additions. And the same is tried for every other task as well. So what we see here is for every data set, each of these model architectures are tried and the scores are reported. Now when it comes to multitask performance, this model is a unified model. That model is trained on all of these tasks, all of these data sets, and the scores are reported. For example, as we can see here for squad, for an architecture with self-attention that is trained on all of these data sets, it gives a score of 66.8, which is not really as good as single task performance, but it is close. So these are some of the results that are reported, but as we can see here, there is a Deca score that is given. So for single task performance, what we have is 513 with this setting or configuration, whereas for multitask, we have something like 546, 533, and 562. Yeah. So here's another example. We have, these are the scores that are reported for single task, 48.2, 68, 74. Whereas for multitask, we see that 66.8, 71.8, and 70.8 are the results that are noticed for multitask. Transformers is benefits in single task. Okay, so I think there are. Yeah, so from all of these experiments, what they have noticed is that adding transformer layers is it is giving better results for single task and multitask setting. As we can see here, with self-attention, we have seen that the score has improved from 48 to 68. So that's an improvement. They have also seen that question pointing to the question is essential. So Q pointer is nothing but question pointer. As we see here, even doing that has also produced better results. Like from 48, using a plain seek-to-seek model gives a score of 48 for squad dataset, whereas using Q pointers, a score of 75.5 is given. Okay, so how about training these models? If here, consider A, B, C, D, E to be different tasks. We have task A, task B, task C, so on until task E. And when training, there are different ways of doing it. One is you take one batch from each of these tasks, like you take batch 1 from task A, and then you take batch 2 from task B, and you repeat that for the other tasks as well. And you train your model. So this is one way of doing it. So this way you get 5 batches from each of these tasks, and then you train the model, and then you repeat for other batches. So instead of that, the authors have also tried another approach where they first order the tasks in the order of difficulty. Like task A is the most difficult of all the tasks, followed by task B. So now the tasks are actually ordered in the order of their difficulty, and then the batches are picked first from the hardest task, and the model is trained. And then the next batch is picked from the next harder task, and that is repeated for all the other tasks as well. We have the results again. So this slide is about the other experiments that were done on this network. So MQAN is nothing but multitask question answering network, something that we have seen in the previous slides. So this is all from the slides. There is also a blog from for the same here. Do you see the blog? Okay, so this blog is again from the same team that worked on this paper. So this is official GitHub page for this DECA-NLP. You can go through this, and here's the blog that is related, that is based on this paper or this work. Yeah, so as we can see here, developing architectures that are very specific to some tasks, they don't really help us with coming up with models that generalize well for other tasks, which is why we need some sort of unified models. And that's why DECA-NLP is proposed. It's actually a challenge. DECA-NLP is a challenge. Yeah. Yes, so it says the natural language decathlon is a multitask challenge that spans 10 tasks, something that we have discussed. So yeah, I'll quickly go through this blog. Yeah, so what MQAN does is that it jointly learns without any task-specific modules or parameters all the 10 tasks. So this image is something that we have seen in the slides. We have different 10 tasks here, and all the tasks are being addressed as a question answering task. So here, each of these tasks are described like question answering. We have machine translation, we have summarization, and we have natural language inference. So what exactly is natural language inference? So what it does is an NLA model. It takes two sentences, a premise and a hypothesis, and then it classifies the relationship, whether is it an entailment, is it neutral, or is it contradiction. So that's what NLI is about. And then we have sentiment analysis, we have semantic role labeling, relation extraction, goal-oriented dialogue, semantic parsing, SQL query generation. So when you say something to the model in plain English, the model will generate the SQL query for that. So there is a dataset called WikiSQL for that. So using that dataset, the model can do this. So this is also part of this unified model. Pronoun resolution. So here we have something about decathlon score. Here's the architecture again, the same thing that we have seen in the slide. So here is a very brief description of what exactly this model is about. So MQN takes in a question and context document. So the question and the context is the input to the model, to the network, and then both of them together they get their own encoding using a bi-LSTM. So that's what they get the encoding. The encoding is done initially. So then we have self-attention here. Yeah. So we discussed this, the pointer, the multi-pointer generator decodes users' attention over the question, context, and previous output tokens to decide whether to copy from the question, copy from the context, or generate from a limited vocabulary. So using this pointer switch or pointer generator, the decoder actually decides whether it kind of weighs between the question that is provided, the context that is provided, and the vocabulary that is available. So using all these three things, the model outputs each word. So here are the results that we have seen. Yeah. So here's another plot. So what this plot shows is that the blue curve is something that shows the results for the model that is pre-trained on DecaNLP, whereas the red curve shows the model's performance whose weights are randomly initialized. So as we can see here, the model that is pre-trained on DecaNLP kind of outperforms the model that is randomly initialized. So this is something, I mean, it's like that kind of a curve that it's comparing between the model which is randomly initialized and the model which is pre-trained on ImageNet. Like let's say we have cats and dogs, and you're trying to build a cat versus dogs classifier. You try two ways. One is you train the model from scratch, and then you train the model using a pre-trained model which is trained on ImageNet previously. And then you see that the model which is pre-trained, which makes use of a pre-trained model, gives us better results and faster convergence than that of randomly initialized model. So that's exactly what we see here, but this is happening in an NLP setting. So that's all about this blog. So are there any questions? Any questions, or is?
So I have a question. So my impression from his lecture was that this technology is not ready yet, and he was kind of hinting to like it might be ready next year.
Yeah, it's not really. I wouldn't say it's ready yet. I mean, it's not something that people are trying at the moment. So as one of the things that was mentioned in the early slides, like we have to get into something like continuous learning for these models to be, deployment friendly, or to get anywhere close to more generalized AI. So, uh, so yeah, that's correct. Multitask learning is not something that is, it's not anywhere close to being widely used. So it's still it's still like in the research phase. Yeah.
Thanks.
Sure. So this is the 17th lecture. We have 3 more, and I guess the rest of the lectures are also going to be like this. Like they talk more about uh, the things that that we can expect to come uh, sometime soon, or the things that are not really uh, explored much yet. I don't know why the slides are taking so much time to load, but anyways, so are there any other questions? And I'm not sure like whether any of you got a chance to go through lecture 17 or not. If I missed something, maybe you can share. There is actually a blog by Sebastian. Yeah. So there is this blog by Sebastian Ruder, who is kind of popular in NLP. He's also like part of Fast AI. He has collaborated with Jeremy. So I'm yet to go through this blog, but it looks pretty good. It covers a lot of things. Like there is something called hard parameter sharing. As we can see here, we have 3 tasks: task A, task B, and task C. But we have these initial layers that are being shared by all the tasks. So this is one kind of configuration. And then there's something called soft parameter sharing, where every task has its own model. There are no layers that are being shared here. So this is another different setting here. So I'm yet to go through this blog in detail. I'll be doing that. Yeah. So that's all I had for lecture 17. I haven't I didn't get started with lecture 18 yet, or else we still have 15 minutes, so we could have started, but we'll be doing it next week. So is there anything else that any of you would like to discuss or share?
Thank you. And yeah, as I mentioned in the beginning, can we try maybe to start half an hour earlier?
Sure. I'll be posting the message right after this session. Yeah.
Thanks a lot.
Sure. Thank you. So if there is nothing, then I think we are done for today. We will be meeting again next week, and we'll be discussing lecture 18. We still have 3 more lectures to go, so yeah, I think we'll be finishing in another 3 weeks. So thank you all for joining. I hope you all had a very good start for the new year. Happy New Year, and see you all next week.